Hi, and welcome to our adjusted R-squared lecture, version SKLEARN. The R-squared is one of the most common measures of goodness of fit. In other words, it is a universal measure to evaluate how well linear regressions fare and compare. Moreover, there is a very intuitive method called SCORE, which can help us with that. Depending on the type of regression you are performing, a regression score will have a different meaning. We will explore more types of scores later on. What is convenient in this case is that we can use the same SCORE function for both a simple linear regression and multiple linear regression. What is inconvenient, though, is that when we are working with SKLEARN, we are compelled to call a bunch of different methods in order to reach the amazing summary which stats models provides us with. Either way, after we cover this section, we will have solid knowledge allowing us to choose our preferred package. Okay, to find the R-squared, let's write reg score x, y. It takes two arguments, the inputs and the target. After running the cell, we get 0.407. Let's compare this result to the stats model's regression summary from last section. The R-squared value we achieved is precisely the same. The good news is that the two packages are equivalent in terms of results, at least for now. The bad news is that this is the R-squared value and not the adjusted R-squared one. As you may remember, the adjusted R-squared is a much more appropriate measure for a multiple linear regression. It steps on the R-squared and adjusts for the number of variables included in the model. If we are using features with little or no explanatory power, the R-squared would increase nonetheless. Thus, we need to penalize this excessive usage through the adjusted R-squared. Unfortunately, there is no ready-to-use method included in SKLEARN. In such cases, there are two options. One, we can Google to check if someone had the same problem and solved it. Or two, use our mad math skills to create our own measure. Let's opt for the latter. I'll turn this cell into a markdown and use LaTeX to write down the R-squared formula. This, by the way, is one of my favorite features of Jupyter. Since it is based in your browser, it has some unconventional capabilities that most of the other IDEs lack. Here's the LaTeX code. By running the cell, the code will compile and we will get a neat math formula. In this formula, n stands for the number of observations, or 84, while p for the number of predictors, or 2. We will now try to create this R-squared measure on our own. Actually, the expression is far from complicated, so I suggest that you stop the video here and try to reproduce it yourself. Alternatively, you may follow our instructions, starting now. First, we need to declare a variable called R2, where we will store the R-squared we found earlier. Next, we must find n and p. The input data is stored in x. X has a shape of 84, 2, so 84 observations and 2 features. To build a parameterized version of the code, we can use the shape function to extract the number of observations and features. The samples, n, are equal to the first dimension value of that shape. So, x dot shape square brackets 0. Analogically, the number of features p is equal to x dot shape square brackets 1. Great, we have all the ingredients. Finally, we can calculate the adjusted R-squared. Let adjusted R2 be equal to 1 minus brackets 1 minus R2 times n minus 1 divided by n minus p minus 1. And that's it. A fun exercise may be to define your own Python function, which calculates the adjusted R-squared given inputs and target. But we can leave that for homework. Let's finally execute the cell. The value we get is 0.392. Usually, you won't be able to validate if this is the correct answer, but lucky for us, we've got our old friend, the stats model's regression summary. Comparing the two values, we confirm that we have worked correctly. Our conclusion is that the adjusted R-squared is considerably lower than the R-squared. Thus, one or more of the predictors have little or no explanatory power. In the next lecture, we will see how to determine which one. Thanks for watching.